India is on a determined journey towards a cleaner and more sustainable energy future. A significant part of this national mission involves the production of ethanol, a renewable biofuel that can be blended with petrol. This initiative, known as the Ethanol Blended Petrol Program, aims to reduce our country's reliance on imported crude oil, cut down on harmful vehicle emissions, and improve air quality in our bustling cities. By turning to our agricultural abundance, we are creating a homegrown solution to a global problem. This strategy not only strengthens India's energy security, but also aligns perfectly with our commitments to combat climate change, making every liter of blended fuel a step towards a greener tomorrow. The choice of feedstock for ethanol production is a critical one, and India has wisely turned to its vast agricultural resources. While sugarcane has traditionally been the primary source, the focus is increasingly shifting towards grains like maize and broken rice. These grains are plentiful, and using them for ethanol production provides an additional stable market for our hardworking farmers. This diversification helps to stabilize farmer incomes, especially when there is a surplus of grain that might otherwise go to waste or fetch low prices. It's a strategic move that transforms agricultural surplus into a high-value energy product, creating a powerful synergy between the farm and the fuel pump. The beauty of the grain-to-ethanol process lies in its circular economy model. It is not just about producing fuel, it is about creating value while minimizing waste. Modern Indian distilleries are designed to be highly efficient and environmentally conscious, ensuring that the entire process is sustainable from start to finish. This means that byproducts are not discarded but are recovered and turned into useful products like nutritious animal feed and industrial-grade carbon dioxide. This holistic approach ensures that we are making the most of our resources, reducing the environmental footprint of the industry, and building a truly self-reliant energy ecosystem for the nation. As we look towards the year 2025 and beyond, the role of grain-based ethanol will only grow in importance. The government has set ambitious targets for ethanol blending, and achieving them will require a massive scale-up of production capacity. This expansion presents a tremendous opportunity for rural development, job creation, and technological advancement in the biofuel sector. By investing in this green technology, India is not just producing fuel, it is building a more resilient economy, empowering its agricultural communities, and paving the way for a cleaner, more prosperous future for generations to come, one kernel of grain at a time. The journey of converting humble grain into high-purity fuel begins the moment trucks laden with maize or broken rice arrive at the distillery gates. This initial stage, known as grain reception, is a meticulously organized operation. Each truck is first weighed on a large weighbridge to accurately record the quantity of raw material received. Samples are then carefully drawn from the load and sent to an in-house laboratory for quality control checks. Technicians test for crucial parameters like moisture content, foreign matter, and signs of any damage. Only the grain that meets the stringent quality specifications is approved for unloading, ensuring that the entire process starts with the best possible raw material for optimal ethanol yield. Once a truckload of grain is approved, it proceeds to the unloading bay. Here, advanced hydraulic tippers are often used to empty the entire truck's contents swiftly and safely into an underground hopper. This minimizes manual labor and speeds up the entire turnaround time. From this receiving pit, a series of enclosed conveyors, such as bucket elevators and chain conveyors, transport the grain to large storage silos. These towering silos are designed to protect the grain from the elements, pests, and spoilage. They are equipped with aeration systems that circulate air to maintain the ideal temperature and moisture levels, preserving the quality of the grain for weeks or even months before it is needed for processing. Before the grain can be milled, it must undergo a thorough cleaning process. This step is vital to remove any impurities that might have been mixed in during harvesting or transportation. The grain passes through a series of specialized machines, including screeners and destoners. Screeners use vibrating meshes of different sizes to separate out larger debris like sticks and straw, as well as smaller particles like sand and dust. A destoner, as the name suggests, uses air currents and vibration to separate heavier stones and pebbles from the lighter grain. Magnetic separators are also employed to catch any stray pieces of metal, protecting the downstream milling equipment from damage and ensuring the purity of the final product. The final step in this preparatory phase is milling. The cleaned grain is transported to a hammer mill, a powerful machine that grinds the hard kernels into a coarse flour or grits. The goal is not to create a fine powder like baking flour, but to break open the grain's tough outer shell and expose the starchy endosperm inside. This increases the surface area of the starch, making it readily accessible to water and enzymes in the next stage of the process. The consistency of the grind is carefully controlled because it directly impacts the efficiency of the subsequent steps. A proper grind ensures a smooth slurry and allows for complete conversion of starch to sugar, setting the stage for a successful fermentation process. With the grain milled into a coarse flour, the process moves into the core chemical transformation stages, beginning with slurry preparation. The milled grain is continuously fed into a large agitated tank called a slurry tank. Here, it is mixed with a specific proportion of water, often recycled from later stages of the process to conserve resources. The mixture is constantly stirred to create a homogeneous porridge-like consistency known as the mash or slurry. Getting this ratio of grain to water correct is crucial for the process's efficiency. Too thick, and it becomes difficult to pump and heat. Too thin, and it wastes energy and tank capacity. This carefully controlled slurry is the medium in which all subsequent biochemical reactions will take place. The slurry is then pumped through a series of heat exchangers and jet cookers in a process called liquefaction. The temperature is rapidly raised to around 85 to 95 degrees Celsius. This high temperature, combined with the addition of a heat-stable enzyme called alpha amylase, works to gelatinize the starch molecules and break them down. The long, complex starch chains are chopped into shorter, more manageable chains of sugars called dextrins. The jet cooker uses high-pressure steam to ensure rapid and uniform heating, which is essential for breaking down the starch granules effectively. This step is called liquefaction because the thick, viscous slurry becomes much more fluid and liquefied as the starch breaks down, making it easier to handle in the downstream processes. Following liquefaction, the mash is cooled down to a more moderate temperature of about 60 to 65 degrees Celsius and transferred to saccharification tanks. Here, a second enzyme, glucoamylase, is introduced. The job of this enzyme is to complete the breakdown process started by the alpha amylase. It meticulously snips off individual glucose molecules from the ends of the dextrin chains. This step is known as saccharification because it converts the starch-derived dextrins into simple fermentable sugars, primarily glucose. The process can take several hours, during which the mash is gently agitated to ensure the enzymes have full access to the dextrins, maximizing the conversion of starch into the sugary food that the yeast will need. Once the mash is rich in glucose, it is cooled further to around 30 to 32 degrees Celsius and moved into massive fermentation tanks. This is where the magic of biology takes over. A specific strain of yeast, typically Saccharomyces cerevisiae, is added to the sugary mash. The yeast consumes the glucose as food, and through its metabolic process, produces two main products, ethanol and carbon dioxide. The fermentation tanks are sealed to maintain an anaerobic or oxygen-free environment, which is essential for ethanol production. This process is carefully monitored for temperature and pH, and typically lasts for 48 to 72 hours. By the end, the sweet mash has been transformed into a beer containing about 12 to 15% ethanol by volume. After fermentation is complete, the resulting mixture, known as beer, contains ethanol, water, and all the non-fermentable solids from the grain, such as proteins, fibers, and oils. The first step in separating the ethanol is to send this entire mixture to a series of distillation columns. Distillation works on the simple principle that ethanol has a lower boiling point, about 78.3 degrees Celsius, than water, which boils at 100 degrees. In the first column, often called the beer column or analyzer column, the beer is heated. The ethanol vaporizes first, rising to the top of the column, while the water and solids, collectively called whole stillage, are removed from the bottom. This process effectively separates the liquid ethanol from the solid byproducts. The ethanol vapor from the top of the beer column, which also contains some water vapor, is then channeled into a second column, known as the rectifier column. Here, the separation process is refined. Through a series of trays or packing material inside the column, the vapors are repeatedly condensed and re-vaporized. With each cycle, the concentration of ethanol in the vapor increases as more water is left behind. This multi-stage distillation process allows for the production of a highly concentrated ethanol solution. By the time it exits the top of the rectifier column, the ethanol has reached a purity of about 95% by volume. This product is referred to as rectified spirit or hydrous ethanol. For ethanol to be blended with petrol, it must be almost completely free of water. The 95% pure rectified spirit is not sufficient, as the remaining 5% water would separate from the gasoline. To remove this last bit of water, a special dehydration process is required, most commonly using a technology called molecular sieve dehydration. The 95% ethanol vapor is passed through vessels filled with synthetic beads, known as molecular sieves. These beads have microscopic pores that are just the right size to trap the smaller water molecules, while allowing the larger ethanol molecules to pass through freely. This highly effective process removes the residual water, resulting in fuel-grade ethanol with a purity of over 99.8%. Before this pure ethanol is sent out for blending, it undergoes a final step called denaturing. This is a crucial safety and regulatory measure to make the ethanol unfit for human consumption and prevent its illicit use as a beverage. A small amount of a denaturant is added. Typically, this involves adding a bitter-tasting chemical or a small percentage of gasoline to the ethanol. This renders the product undrinkable without affecting its performance as a fuel additive. The denatured anhydrous, meaning water-free ethanol, is then stored in designated certified tanks, ready to be transported to petroleum terminals for the final blending with petrol. A truly sustainable grain-to-ethanol plant operates on the principle of a circular economy, where waste is minimized and byproducts are transformed into valuable co-products. The most significant byproduct from the distillation process is the whole stillage, the non-fermentable mixture of water, protein, fiber, and fats left behind after the ethanol has been separated. This material is far too valuable to be discarded. The whole stillage is first processed in a decanter centrifuge, which spins at high speed to separate the suspended wet solids, known as wet cake, from the liquid portion, called thin stillage. This initial separation is the first step in creating a highly nutritious animal feed. The separated wet cake is rich in protein and fiber, but it still contains too much moisture for stable storage. It is conveyed to a large rotary drum dryer, where it is tumbled and dried with hot air. Meanwhile, the thin stillage, which contains dissolved solids and nutrients, is sent to a multi-effect evaporator. This system uses steam efficiently across several stages to boil off the excess water, concentrating the liquid into a thick, nutrient-rich syrup. This syrup is then mixed back with the wet cake just before it enters the dryer. This process not only conserves the valuable nutrients from the liquid, but also helps in the drying process, creating a final uniform product. The final dried product is known as dried distillers' grains with solubles or DDGs. This co-product is a cornerstone of the economic viability and sustainability of a grain ethanol plant. DDGs is a highly sought-after commodity in the livestock industry, valued as a high-protein, high-energy ingredient in feed for cattle, poultry, and fish. It provides an excellent alternative to traditional feed components like soybean meal and corn. By converting the leftover grain solids into DDGs, the distillery creates an additional revenue stream, reduces waste, and contributes to the food supply chain, making the entire operation more profitable and environmentally friendly. Another significant byproduct generated during fermentation is high-purity carbon dioxide, or CO₂. For every liter of ethanol produced, nearly a liter of CO₂ is also created. Instead of releasing this greenhouse gas into the atmosphere, modern distilleries capture, purify, and liquefy it. This captured CO₂ has numerous industrial applications. It is used to create the fizz in carbonated beverages, for flash freezing in the food processing industry, and in the manufacturing of dry ice. By capturing and selling this CO₂, the plant not only prevents emissions, but also adds another layer of revenue, turning a potential pollutant into a profitable product and further enhancing its green credentials. The modern Indian grain-to-ethanol facility is a marvel of engineering, a far cry from traditional distilleries. At the heart of its operations is a sophisticated automation system known as SCADA, which stands for Supervisory Control and Data Acquisition. This centralized computer system acts as the plant's brain and nervous system. From a single control room, operators can monitor and manage every aspect of the process in real time, from the flow rate of the grain slurry to the temperature in the fermentation tanks and the pressure in the distillation columns. SCADA systems use a network of sensors and automated valves to maintain optimal conditions, ensuring safety, consistency, and maximum efficiency around the clock. This high level of automation is crucial for maintaining the stringent quality and safety standards required in the industry. The SCADA system continuously logs data, allowing for precise process control and immediate detection of any deviations. If a temperature rises too high or a pressure drops too low, the system can trigger an automatic shutdown or alert an operator to take corrective action. This minimizes the risk of accidents, reduces the chance of a bad batch, and optimizes the use of energy and raw materials. By replacing manual interventions with reliable automation, modern plants can run more smoothly and produce a higher quality of ethanol consistently, which is vital for large-scale fuel blending programs. Sustainability is another defining feature of the contemporary Indian ethanol plant, with a strong emphasis on water conservation through zero liquid discharge or ZLD design. A ZLD system is an engineering marvel designed to recycle and reuse every drop of water within the facility. Wastewater from various processes, such as cooling tower blowdown and equipment cleaning, is collected and treated through advanced methods like reverse osmosis and evaporation. The purified water is then looped back into the process, for example, in making the initial grain slurry. The small amount of leftover solid waste is disposed of responsibly, ensuring that the plant does not discharge any liquid effluent into the environment. In conclusion, the grain-to-ethanol process represents a powerful convergence of agriculture, technology, and environmental stewardship for India. By transforming surplus grains like maize and broken rice into clean-burning ethanol, the nation is taking decisive steps to enhance its energy security, reduce its carbon footprint, and create a cleaner environment. This process provides crucial support to farmers by creating a stable demand for their produce, while the recovery of byproducts like DDGS and CO₂ exemplifies a commitment to a circular economy. Guided by modern automation and a firm commitment to sustainability through ZLD, India's ethanol industry is not just fueling cars, it is fueling a brighter, greener, and more self-reliant future.